Welcome everybody to the panel on model-based systems thinking. We're excited about this topic. I'd like to talk to you about it. It's not a typical terminology used, but I think you'll know what a really nice panel here for us today. Alon, if you can go to the introduction slides. Okay. So I'm Kamran. I'm a systems fellow at Woodward, and I'm also a professor of systems engineering at Colorado State University. I'm one of the founders of that system engineering program in 2009, which has now grown to be one of the largest in the nation. Should I continue and introduce themselves? How does that work? Which is better?
Sure.
Okay, go on.
Yep, I'm Golam Boktir. I am a systems engineer in north of Grumman. I've been in the aerospace and defense industry all my career. I am currently a PhD candidate under Dr. Shahroudi at Colorado State University, and my research interest is in wildfire UAV fleet design and deployment.
Great. Quentin, go ahead.
And greetings, everyone at INCOSE. My name is Quentin Salter. I am a senior program officer at the Office of Naval Research. I'm also a PhD student under Dr. Shahroudi, and very interested in systems dynamics. Currently, my PhD research is on innovation and the S&T ecosystem of the Department of Defense. And thank you for joining our panel today. Can't wait to get into these really good discussions. And I think up next we'll have Ms. Sarwat Chappell.
Hello, everyone. I'm Sarwat Chappell. I'm a program officer at the Office of Naval Research, and I manage S&T programs for the Navy. I'm a PhD candidate at Colorado State University with Professor Shahroudi, and my PhD thesis is related to the complexity and dynamics of endurance performance. Looking forward to a robust discussion today.
I'm Kirk Reinholz. I was a principal engineer with NASA for a long time. I've got code orbiting various other planets. But a few years ago, I realized that the world has moved a whole lot forward from kind of what I look at as 20th century engineering. So I left the lab and came back into the PhD program, another one under Professor Shahroudi, to essentially catch up and even push forward to see what can we do with 21st century capabilities with respect to system engineering.
Excellent. So one thing I want to add, everybody here, I mean, we all have an academic connection, obviously, but everybody here has been dealing with real world challenges, complex real world challenges, and several of us have moved into multiple domains, into different industries or different application domains, different types of challenges. So even though we do have the academic connection, we actually have our focuses, and also the research focus of the various folks here are on real world complex challenges. Okay, so that's important to note. Next, Kamran, please. Okay, so we have a few key questions. And by the way, one of the reasons we're here is not to just talk one way. We're definitely interested in your reflections or feedback and/or questions on comments, either on these questions or anything that you think would be appropriate. But here's what questions we've prepared right now. What are the rigorous frameworks, languages, and tools for model-based systems thinking? What are some examples of real-world applications of model-based systems thinking? Is system dynamics almost synonymous with MBST? A lot of people think so, and the way they talk and present is they may not say this, but it may be implied. Is MBSE rigorously enabling systems thinking? This is MBSE, not MBST on question 4. So this would be things like architectural modeling and Cameo systems modeler, for example, or various tools that we have, which we consider falls under the MBSE banner. Then shall MBST be discipline agnostic or specific? And then why is the adoption of system dynamics so low in mature industries? It's true that when you go to mature industries, go to Airbus, GE, Boeing, Cummins, Caterpillar, you name it. You don't see many people doing this. They may have consultants that do some of this, but it's not really penetrated. So we're trying to answer some of those questions. And that last question, the why, will lead into what we think is coming. So the last speaker, Kirk, will talk about what we believe will come in or is in the future of system dynamics and MBST. Okay, next. So we have a set of presentations for you, and I think what we're gonna do is do one quick presentation per person, and then we will pause after each presentation and let you ask your questions. If you like to put your questions in the chat, that would be great. I won't be able to see them live, but we will monitor them, make sure they get answered. So we're hoping that we'll go through, each one of us will come and give our opinions on these questions, and then the floor is open for you to interact with us. Before we get started, are there any thoughts or questions from the audience or from the panel before we get going? Is everything pretty clear what we're about to do? Guess I can open the chat box here. Okay, overview of rigorous modeling methods for systems thinking. Go ahead. So before we get started, just a few things, just few minor definitions. I'm not a big person on definitions, but I think just getting a few things so at least you know where my thoughts are at. Model-based system thinking, in my view, is rigorous application of systems principles to solve real-world problems. So it's a pretty generic statement. It does not imply a particular modeling technique. The rigor comes from discipline agnostic modeling methods. So we're applying frameworks, languages, and tools that don't really care about what discipline you are, what domain you are, what application areas. And in fact, typically our challenges fall into multiple domains. And we don't control how the challenges show up. So it has to be discipline agnostic modeling methods. And then MBST rigorously updates the mental models with high leverage influence strategies. So what that means is that the whole point about this MBST is so that we improve the way we think about or we understand complex challenges and problems. And by exercising these rigorously, there are rigorous tools that will help us improve our mental models of the problem in the hope that we improve our chances of interfering with them, improving them, solving them, and so on. And it helps us find points of high leverage. So interfering or interacting with complex issues and problems, as you know, is not easy, and not every point of interaction has high leverage. So we want to find the best places to interact so that our efforts are spent well. And basically, the strategies that come out of this will be anything that will change the purpose, structure, or patterns of behavior of the system we're looking at. Next. So in my view, there are actually a lot of modeling methods out there, but really system dynamics is very mature and has been applied with to a lot of different areas. It has not penetrated industry much beyond consultants and so on, but at least there is quite a lot of applications and good use cases from system dynamics. So that's definitely at least one of them. Design structure matrix or N2 diagrams is a way to visualize and optimize the architecture. It's probably the simplest method I know, but it also it's very low penetration. Not many people are doing it. Architectural modeling, SysML, model-based system architecting process, and things that you can do with Cameo, for example. All of that I'm calling architectural modeling, and this is getting a lot of usage, but I consider this to be one of the modeling methods that is good for MBS, for systems thinking, and as long as it is done in that way. Just picking up and doing SysML does not necessarily lead to better systems thinking, but if it's part of the framework for systems thinking, it can be very helpful. We also have stochastic modeling, agent-based modeling, AI, machine learning, symbolic math, and causal inference or graph analysis. And today we will show you different applications. Each one of the talkers will come and show you a different application where maybe 1, 2, or 3 of these have been used. So I will start with a couple of examples, but then every person who talks will bring a different type of application and then different set of tools that they've used. So we are not really worried too much about which exact tool, but we just want to make sure you know about what are available and then how you can bring it under this systems thinking banner to help with the complex problem. Next. So the first example I'll show you is a real world example. This is a max transport in Fort Collins. If you go to Fort Collins, you will see this line running north to south, but it started service in 2014, and it had the ridership curve of it over time. It had a particular shape. And it was interesting to try to understand that shape, but also it was interesting to try to see if the ridership could be improved. There is always like something exciting is introduced and you have an initial spike in ridership, but then it was plateauing. And then the question was, how can we boost that ridership again? And also trying to understand how ridership of the meth was impacting car traffic in the city. So few people who were connected with the city started building a system dynamic model. This was back in 2014. And the model, it was a system dynamic model. It helped them understand the patterns of behavior of ridership and effectiveness. And also they understood a little bit how it impacts car transportation and where to put their money, where the city should put their money to expand it. If you go to next slide, Kamran. The model they built was not super complicated. It was part of it is on the left. It was the basic adoption loops. And then they added some simple car traffic loops and some policy loops. So altogether, they didn't have more than, I think, 7 or 8 major loops in their model. But that was enough. If you go to the next slide, that was enough on the left to understand the current behavior. So you see that attractiveness initially shot up after introduction, but then plateaued. And then you can see the ridership numbers also plateauing. And then you see that the ridership shoots up to about 100,000. And then at 36 months, the impact of doubling capacity is to increase ridership, but it doesn't have it. Doubling capacity doesn't lead to doubling the ridership for a lot of the nonlinear reasons that was modeled in their model. So these are the kind of things that that they use. Today, it's, I think the ridership is at 400,000, 450,000. So this is an example of a real world result where there is a real world system, and people involved with it are using models to better understand the complex behaviors and making decisions based on that. If you go to the next one, this is another example. And actually, the person who did this is sitting right next to me. It's another real world example, a clinic, a medical clinic, imaging clinic in California. And on the right-hand side, you see this pattern of behavior, which is the percentage of patients that are same-day missed, or people who have made appointments and then don't show up. Lower on the right, you see that this is year over year, it's costing the clinic. This is just one clinic. It's costing the clinic significant amounts of losses. And so what the researcher did, who was Jill Spiess, she created, she solved this kind of in two ways. She used a predictive model, which is kind of like AI machine learning, and combined it with architectural modeling in Cameo, and then came up with some solution that they actually implemented in the clinic. If you go to the next slide. So the top one was a model they made for just training and validating the predictive model, so that if a patient was calling to make an appointment, then the scheduler would be able to predict the probability that they would miss the appointment and why that would be. And then Jill and Leo implemented it so that it was actually there was an implementation version of this that was actually part of the scheduling system. By the way, you can correct me if I'm doing anything. And if you go to the next chart, so they combined that with architectural modeling to find out, to design a solution for the changing the way they schedule and they interact with the patients. And then actually they measured double-digit savings in the losses that they had. So for this clinic, it came up to about $260,000, which was very significant. And it's an example of kind of advanced work, systems thinking work, augmented with good modeling, and then good modeling methods, and then giving some real world benefit. Okay, if you go next. All right, so starting to answer a couple of the questions, and then we'll open it up to the floor for a few minutes before the next speaker begins. Is system dynamics synonymous with MBST? I don't believe so. I think it depends on how system dynamics is utilized. It is true, it's a favorite, it's very mature. Since Sterman published the year 2000, I was taught by Sterman, but it's very capable. It has very broad range of real world applications, but it's very difficult to master. It's not intuitive and it's not natural to most people. And you really, in order to be able to do a good job of it, you really need to invest reasonably heavily into it. And not only in classes, but also like Jill having exposure to a real world problem where you can exercise it. We recognize system dynamics and a whole bunch of other tools, architecting tools, machine learning, graph analysis, and we recognize that all of those are actually now part of the model-based systems thinking tool set. And the framework should build on and expand beyond just system dynamics for more effective adoption, we believe. Just like the example I showed you, for example, Jill had to combine a couple of these modeling methods in order to have a good hit on the problem. Next. Is MBSE rigorously enabling systems thinking? So first of all, I want to make sure that we say that MBSE or SE is not the same as systems thinking, And we actually had, if you can watch the video of Mike Jackson, he was a keynote speaker, and he actually highlighted very eloquently that system engineering is actually not capturing a whole bunch of concerns related to systems thinking, and which was wonderful to hear. If you haven't seen it, you should see it. And my opinion is SE is process and machinery, is like systematic, and systems thinking, though, is the philosophy and the way of approaching complex problems, in the hope that our odds of we find some leverage points or our odds improve in some way. I believe successful system engineers need systems thinking for sure, but successful systems thinkers may have never heard of even system engineering or MBSE or any system engineering handbook and so on. And in fact, I have experimented with this, giving system engineering handbook to people who are not in the field, and they will just not know what to do with it. So I'm really now MBS. We have a lot of tool vendors, and they're selling MBSE tools, very good ones, and getting better all the time, like Cameo, System Composer, System Modeler. And there's a whole bunch of things that help us with architecting modeling. And I think that unless they are specifically consciously used as systems thinking tools, they don't naturally lead to system thinking. I have examples of students that have gone through system engineering education very well. They've gone through MBSE architecting classes very well, and they are able to create artifacts that look great in SysML, but it lacks understanding. It lacks that systems thinking, and is not really helpful to the problem that they have on their hand. So this is just a few of my opinions, and I think that's. Do we have another slide here, or is this my last one?
That's the last one. Should we take a couple Q&A?
Yeah.
Right?
Oh, yeah, great. So this is now, we don't want to just for the speakers to talk. Really, any question is a great question, and any comment, question, thoughts, please go ahead and bring it forward. And otherwise, I will start picking on you guys. So go ahead.
I had one thing I guess I'll throw in there. This is Eric Dano from GW. My experience in doing mostly architecture, defense systems, I think they're coupled. If you drew a Venn diagram between systems engineering, system thinking, especially system architecture, because to me it's a triangle. You got the inputs, you got the requirements, and you got that decision analysis piece. And systems thinking is absolutely critical to that systems thinking, abstract thinking, holistic thinking, to really make it a complete, robust architecture, especially when you look multidiscipline over the life cycle. You know, and if it's a socio-technical system, now you have cultures and politics working their way in. So that's all through systems thinking. So I see them as very coupled if you're doing the decision analysis correctly. Now, in inspecting a lot of architectures at architecture review boards, I see that's often missed, or the weak side of the triangle.
Which part is the weak side typically? Which one of those?
The decision analysis. And it's tough in complex systems and system of systems. And that's why, you know, we stress, you know, whatever your domain is, you really have to know it, you know, as well, you know, system thinking, you say, is a domain element. You really have to know it, because if you don't know that, and simple things like even brainstorming, you know, I've seen people get really chopped up. Oh, we didn't know that, we didn't think about that. And there's, you know, obviously a lot of literature out there about engineering, quote, successes that turned out to be total failures, mostly in like socio-technical systems, because they failed to consider stakeholders. They failed to consider elements of the system. So I see them very coupled, and
yeah. And yeah, I tend to agree with you. For there is a whole class of problems where including like um, the same day miss appointment problem. These classes of problem that have a strong element of architectural and human, strong, there's a human complexity in it, there's architectural and behavioral. And so that's why she also did, like you were saying, she combined multiple methods in order to be able to get a handle on it. So we are not into saying, oh, just do architectural modeling or never do architectural modeling. We just have to take a right sweet, as long as we have the mindset correct, I think we would be successful in picking the right ones, probably. Thanks, Eric. I appreciate that. Carolyn King, do you have a question?
Hi, no question.
Okay. Anyone else has one before we move on to the next? So we got Mike, Jacob, Robert, Martin. Go ahead. Don't worry about interacting with us. We are very nice and friendly.
We're extremely friendly.
Yes.
I'll expand more on what Eric had to say, and Eric, I still hope you're still listening.
Yeah. Go ahead. That'd be great, actually.
Yeah, I think we both work in the same field within the Department of Defense. One of the things that systems thinking can bring, which we don't see, is that as you well know, especially when we get to architecture of systems, we're very monolithic in how we go about design and producing and or testing those systems. One of the things that we always seem to do in the Department of Defense is we're always fighting past wars and battles. We don't enable the future capabilities, i.e., what systems thinking or model-based systems thinking can bring to us is that we can update our information for predictions of the future. And that seems to be lacking a lot what we do. We're always, due to the complexity of how the Defense Department works, we're always seem to be catch-up mode or doing things in a catch-up mode. And I believe that as we implement more of the disciplines of the dynamics of system thinking, not only will we be able to do today's and tomorrow's, but even 25 years from now type issues that we can start working on right now. One thing I used to always say in my program, and I'll get a little bit more into it when I go through my presentation, is that we're winning the battles of the future in science and technology investment. We're not winning the battles today. We're winning the battles of the future. And that's a mindset. That's a systems dynamic mindset. You really, truly don't understand that mindset, then you don't really understand what our job should be, or how we should be designing, how we should be developing, how we should be using all these rigorous dynamic tools to improve what our future outcomes be. But any questions on that? Anybody wants to expand on that? Is that a good place for systems dynamic? Anybody want to answer that question?
Well, just one comment on what you said. I totally agree with, and I think, in my opinion, one of the biggest problems is SysML is very great and the tools are great and they're getting better, but I still think we suffer from lack of methodology, which SysML by design is methodology-less. If you look at things like Arcadia Capella, it kind of bakes that in to make sure you get a good architecture, and it kind of forces you to do this systems thinking if you're going to progress step through the ADM. I think that is really the biggest thing that we have missing. And I agree, you don't want to constrain design and you don't want to constrain architecture, but I really think at that first step that everyone's seen the curve from DAU where 70% of the system is driven by your architecture.
Yeah.
We should have some tenets of goodness there, including systems thinking, to get that done. And even if it's a line item in a defense checklist for SFR or SRR, it's something that you could hold people against. All right, what did you do system thinking wise? You know, do you have meeting minutes from the brainstorming sessions, or, you know, did you have the Kanban board, or, you know, Kano, or whatever, you know, technique you want to try? Do you have that? Did you think about what you did, as, you know, on the left side of that V, so that now integration's easier, and then as we take those good products and play them forward into leverage, we're doing exactly what the gentleman said.
Great. Actually, I love it that people raise questions and the panel jumps in. That's great. Anybody else? We can move on to the next speaker unless there is any questions. Okay. Let's move on to Golam. Go ahead, Golam, please.
Good morning, good afternoon, everyone. Thank you, Dr. Shahroudi and panel and everyone, audience, for joining today. One thing I wanted to mention, Dr. Shahroudi coined this term, model-based system thinking, around 2009, 2010, and start teaching this in the systems thinking and system dynamic classes. And so our panel is based on some of the items that being taught at Colorado State. So I will talk a little bit more on the MBST framework, and that is developed by Dr. Shahroudi, and applying that to a research project, UAV fleet deployment for wildfire detection and communication. So this is the framework for MBST, and essentially this framework ensures that we are taking systems thinking principles and walking through a rigorous and defined phases and steps and achieve the desired outcome for a real world problem. The framework is structured around two loops. This is the broader loop, and in a way, this is the slow learning loop. This loop is where the problem definition, hypothesis, or purpose of the investigation may change depending on the initial results or outcome that you get. And then there is the second loop, which is part of the broader loop, is the first fast learning loop, where we refine our understanding of the complex phenomena and policy and controls that impact the mental models. Essentially, this is the fast learning loop. So we don't have to entirely capture, like memorize this whole step. We're going to go through this real quick, and then I'll show that how in our research project we're applying that to a fleet of UAVs that are being deployed as a real world example. So first, on the top left is the basically defining the problem and using an iceberg principle. And anyone familiar with system thinking, very familiar with this concept on the mental model. Then identifying patterns of behavior, such as any sort of exponential growth, goal seeking, overshoot, and such. Third phase is constructing causal loops. We're understanding the different types of dependencies. And fourth phase on the bottom right is understanding the stocks and flows, and that leads to the fifth phase in a middle bottom. Now, this is what Dr. Shahroudi was talking about in different types of models that you can apply. And if you look at, hard to see a little bit of an eye chart. The bottom left is the architectural model. This one of the architecture model types of model is SysML or using MBST, and then you have stochastic model, agent-based model, AI or machine learning model, and system dynamics model. I'm not going to get too much deep into it, but just to touch base on the final phase or sixth phase is where we do mental model and sensitivity analysis using reference modes. This step involves conducting sensitivity analysis to understand the reference mode and loop dominance and understanding different types of scenarios and such. So just briefly wanted to show the framework. How do we learn what we talked about, the model-based system thinking? And this is a very step-by-step framework that allow us actually a lot of flexibilities. And so this is the slow learning loop, the summary of what I kind of just mentioned, and this is the description of the fast learning loop. So again, I'm not going to go too much details into it. Rather, I would like to show you how am I implementing this part of the wildfire UAV fleet deployment. So first question can be is to me, how does this MBST framework can help me do a real world complex problem where I'm trying to design a whole fleet of UAVs and deploy them and be successful, right? So the items that I really need to consider and what the MBST can do for me is the holistic understanding of the wildfire detection and communication. It can help me understand the different scenario planning. And like very important part that we miss often is the identification of the leverage points. So this helps me to help us to understand the leverage points. Then look into deployment optimization. And one of the more important steps, wildfire risk management. And then the stakeholder communication due to wildfire. So this is basically some of these things we desire to achieve. And now, if I were to take the framework that I presented, the generic framework, to this wildfire UAV fleet deployment, how would I go about it? So first, the setting clear goals for wildfire detection and communication. Utilizing the system principle, we can adjust our mental model. And primary objective is here, detect and communicate wildfire using a fleet of UAVs, right? So we refine that process and understand, adjust our mental model using the systems principle. So this is a set of system principle Dr. Shahroudi has developed and that are used part of this model-based system thinking framework. Next phase is the framework. We identify relevant reference mode. One of the data and reference mode that we used was Bell 206 helicopter that to see the climb pattern in the harsh environment to understand the behavior of the vertical lift. There's not a whole lot of data that are available in the eVTOL industry that can show the vertical lift in harsh environment, but Bell 206 has tons of data to characterize that, and that those are publicly available. Next, we look into establishing causal relationships for fleet deployment, and some of the causal relationships such as UAV launch failures, maintenance, UAV climb rate issues, just to name a few. On the bottom right is we looked into stocks and flows, like amount of UAVs that are available, or UAV launches, and repairs, and this is where things get a little bit complicated. Is the UAV design to address the climb, altitude issues in harsh environment and have efficient L over D, lift over drag, and fuel and energy uses. Those are so critical. And walking through this framework help us to understand those. Now, looking to the modeling side of things is out of several sets of models that are discussed, we have done 2 models so far, which is the architecture model, MBST, using SysAML. We have developed a comprehensive enterprise level UAV fleet model, as well as a model for flight controls and vertical lift for using MBST, surface-less flight control. And we are able to actually present that work in our previous INCOSE IS at Hawaii, and that was on flight controls for a wildfire. And ironically, a couple of weeks after our presentation on the wildfire, there was a pretty bad wildfire in Hawaii, which was pretty devastating to see. And then we have developed system dynamic models, which characterize launch submodule and climb submodule. So these 2 are completed, architectural and system dynamic model. We're in the 3rd one that we're working towards is optimization model. It's a set of mathematical model as well as a programmatic model that will work. So the optimization model that we're currently working on is goal would be to minimize risk factor, maximize coverage area, minimize coverage time, minimize total operational costs, and such. So those are, we should be able to adjust all those if we go through this broader loop, as well as on the bottom left, the fast loop. System dynamic model help us to understand the UAV deployment issue over time and potentially explore aerodynamics issues that we can run into. And if you look at on the right side, where we're showing the different models that came into and went through this refinement process, is the system dynamic model, architecture model. Those are 2 completed, and the in progress is the optimization model. And one thing it allowed us to do is incremental verification and validation of the system as we go throughout this loop. So now I wanted to just touch base, like, okay, so we have this MBST, we can go through this modeling and make sure we ensure to get our mental model implemented part of our design, even if we have to go through a couple slow iterations and fast iteration, right? What are like one of the examples that can ensure that we are going in the right direction? So one of the part of the fast learning loop is the reference mode. So we took the Bell 206 data and look into how it performs under harsh conditions. And we took our design architecture and look into that, can we match Bell 206 performance, aerodynamic performance, and we are able to do so on the right. So the right one is our actual design for aerodynamic design for the UAV vertical lift. On the left is the Bell 206 data. So anything that we're designing, it ensures we're living in the real world. We're just not hypothetical scenarios floating around. And on the right, this is the system dynamic model that we have developed, and I think we'll see some of the a little bit few more of the examples as we go through. I am approaching towards end of my discussion, and one thing I would like to discuss is, or answer here, is model-based system engineering rigorously enabling systems thinking. So if you notice that I try to capture attention between E and T so that we're not confused. So model-based system engineering, it works, meaning that, yeah, you can develop a model, no problem. But is it efficient? How can we guarantee that? Someone could be efficient at doing Capella or Cameo or SysML, but may not ever needing to employ system thinking to the best leverage point, right? And Eric Donald, you were just mentioning this Venn diagram of three things. I hope this is close to something that you were envisioning, is that these three Venn diagrams where, yeah, MBST alone can provide you an architecture model, right? It can give you all the elements that you need, right? But is it the most effective? Is it the most efficient? Are we utilizing our mental model exactly that we want it to do? So the solution to that is the MBST. On the bottom right, MBST. So we kind of, throughout this presentation, we have to keep an eye on MBST and MBSC. So MBST provides higher assurance. It has a very focused areas. So for the case of wildfire UAV, we find out that the climb rate is the critical part of all this. The vertical lift that is controls the climb rate, and that could be designed in fanning wings flight control systems. So essentially, the MBST is enabling the not only model-based system engineering, but is incorporating, ensuring that systems thinking is part of that. So right now, I will introduce our next speaker. Actually, I want to see, is there any questions?
Yeah, I highly encourage questions. If there are any.
So I do have a question, if you don't mind going back, I think maybe one slide previous to this one. 2 slides, I'm sorry, go back one more. Because model-based system thinking is brand new to me. So as I take a look at this, let me echo back and make sure that I'm understanding. In the systems principles piece in the upper left, what we're talking about there is you may have a particular challenge or a particular problem or a particular improvement, in this case with wildfire UAV fleet deployment. And in that systems principle piece, you're basically gathering all kinds of different sorts of information that you're then going to put through this cycle to try to discern, where could I seek improvements? Where could I seek to solve problems? Am I getting that correctly in terms of how this is supposed to operate then?
Yeah, absolutely. So this is the generic MBST framework. What we're looking at, slightly modified for wildfire UAV. Right over here, what we're gathering, we gather is what is our mental model that wildfire detection and communication, and understanding what are the things that are structurally impacts that mental model, and what are the patterns that are there. So essentially gathering all those information and walking through this this iceberg concept, utilizing the set of principles that we have, and which is part of Dr. Shahroudi's principles that are taught in systems thinking and system dynamic classes. So taking this generic framework and applying to the wildfire example, we walk through, that's what we capture here.
Got it. Okay, thank you.
Thanks, Michael. Well, who else? Any other thoughts? Or, by the way, you don't have to agree with everything you see.
We're all here to learn as well. So
Yes, yeah.
I was gonna say, at this point, I'm just trying to understand and comprehend what you're saying. So,
Yeah.
I'm just asking you to dumb it down a lot for me, so I'm tracking with what you're saying.
I'm
No,
going to try to give a simpler explanation of model-based system thinking. I think I'm getting ready to come up next, and hopefully that'll
Okay.
answer your questions doing that.
Perfect. Perfect. Anything to help us understand,
Yeah.
simplify this better.
Especially
Okay.
because thank you, Ghulam. Your presentation is awesome, but Ghulam hits on something that's really very important and indicative to model-based systems thinking, and that is systems principles. And it is those systems principles that Dr. Shahroudi drives home in his classes, and that we try to drive home in systems dynamics. And so, next slide, please. I think I already introduced myself. I am Quentin Salter. I'm a program officer for the Office of Naval Research. My responsibilities are to fund research and scientific and technology development programs, have a portfolio of different science projects, engineering projects, enterprise projects. And the biggest question that I get asked from stakeholders, which is warfighters, industry, Congress, is, what is the return on investment, and how do we improve the return on investment? I.e., how do we get innovation out of all the investment that we do for the Department of Defense within the Navy and broader wide? And to understand that, to understand how do we answer the question of what we're spending all your taxpayers' dollars on in innovations and technology and engineering, we have to solve the question of what is innovation. Why do we think that if we take billions of dollars and put it on certain things, we can get some return on it in the future? And I kind of alluded to that in a previous discussion, that it is very important for us to understand, what are the dynamics of the systems of innovation in S&T. And part of my research is to study this innovation ecosystem, S&T ecosystem. In doing that, though, the questions and the observations that have to be answered is, how do we think about innovation? And what Dr. Shahroudi has come up with as far as model-based systems thinking, as Ghulam indicated years back, is actually a very, if you drill down on it, it's a very innovative concept. It's a very innovative philosophy. I denote this philosophy as akin to Aristotle's philosophy, Aristotelian philosophy, syllogistic philosophy. When you think in models, then you can think in ways to solve dynamic issues and problems, not only of present day, but in the future, because that's what dynamics means. In the future, things go along in time, things change. What can you do for predictions of solving those issues? So model-based systems thinking is a way to actually look at the causation of things and not just the correlation. And when you're just looking at correlation, you cannot really truly understand the complexity of systems. You also need to understand their causation. Next slide, please. Come on, next slide, please. Thank you. So I developed a preliminary model of the S&T ecosystem. And as you can see, this is a very complex ecosystem. It involves looking at funding decisions. It involves looking at capabilities of academic, industry, government laboratories, and it also looks at what is the workforce that's involved in all of those things, from uh, industrial researchers, academic researchers, students involved, and then the actual Department of Defense science and funding ecosystem. You know, how do we get things? How do we actually motivate the science? How do we get this science to the point where it is something that can be translated into usability for the warfighter or the stakeholder? Next slide. What we have found in some literature and some of the literature research is that our science and technology investments aren't as disruptive. And disruptive means changing the ability for us to do something different in the future. They're not as disruptive as anyway hypothesized they used to be in the past. You know, and so in this slide and some of the papers that you can read if you go online and you do a literature search, you'll see this thing about disruptive indicators. And these disruptive indicators are based on citations and patents and looking at the numbers of how those things have changed over time to give us bigger capabilities in the future. And you know, it is showing that there is a decline in this from some of these literature searches anyway, about what disruption is. And so in my research, I decided, you know, since I'm looking at this entire science and technology ecosystem, what is causing these indicators to drop, more specifically, but all these indicators, good indicators of innovation being done in our science and technology and ecosystem for the department. Yeah. Next slide, please. So in trying to grasp the breadth of innovation, which I think is when I first thought about this, I thought this would be something that would be an easy thing to find a metric for and point to. But what I really found out is that there is no true definition of innovation that is accepted amongst all breadth of disciplines within science or engineering. And so, you know, in trying to grasp, you know, how do we actually measure innovation and how can we actually predict innovation, I started looking at what causes innovation. So there's a lot of correlations, all right? And this is, once again, where model-based system thinking really comes to an understanding of how to use systems principles like systems are made up of many elements. Systems have a purpose. Systems have a structure. Systems then have their own behavior. Did it go dark on us there? Okay, there we go. Systems then have a behavior. Understanding some of these basic systems principles, that systems evolve and things like that, helped me, at least in my research, in trying to understand causal relationship of how a system can be affected to cause an innovation, or how different effects of a ecosystem can hinder innovation. Correlation is I would like to say something that we use in engineering all the time. We look at the correlation of things. One thing is correlated with another, but correlation is not causation. And I know it's a very simple example when we think about it, and we use this in our classes, and I use this all the time. But when it gets hot, because it's getting hot right now, when it gets really hot outside, you know, there are two things that actually really happen. People buy more ice cream. For one thing, people buy more cooling things. They buy more ice. You eat more ice cream in the summertime than you do in the wintertime. But also, if you look at some of the criminalities, crime also goes up in the summertime. And so, when you think correlation, is there an exact is there an exact causation between buying ice cream and increased criminal activities in summertime? Well, no, no. Using model-based systems thinking can actually give us the causation of why people buy more ice cream in the summertime and also why crime goes up in the summertime. And thinking in models is the key. And as I say, typically, since prehistoric times, which is, we needed to, as a species, we correlate things. And correlating things actually gives us an advantage and has given us an advantage. But as we have developed more complex technologies and systems from enterprise systems, business systems, social systems, correlation seems to not be all that we need to understand what the effects of these things are in the future. It is definitely what causes one thing to happen versus what are the correlations between two things. Next slide. In my research and looking at innovation, one of the things that I had to do is I had to build this model, this model-based systems thinking analogy of innovation and what causes innovation. And in doing so, and in needing models, I had to put together an idea. I had to come up with a hypothesis of which model-based systems thinking is directly linked to. And I'll get into that in the next slide a little bit deeper. Also to help answer that question that you posed previously. But in doing so, I base first of all the definition of innovation as if a Nobel Prize researcher is doing something that is innovative, then they're going to receive that Nobel Prize. All right. So I start with a very simple premise, and then can a model be built to show what the causations is of that Nobel Prize research on innovation for today and in the future? And so I did build a simulation in which I could predict Nobel Prize research and how that research responds over time. Next slide, please. In doing so, though, I had to actually have a model. I had to think about innovation in a model fashion and not in a correlation fashion. In a couple previous slides, I showed the disruptive indicators, which were our correlation factors. All right, these are, what is the correlation between the number of patents being produced versus the number of new inventions coming out. But in thinking of the causation of innovation, I had to build a model that, what actually causes an idea or an innovation, a technology or a system to change over time. And in doing so, I had to use systems principles. And in looking at those systems principles, I had to think about, all right, in building a model and how to think in models, what is the effect of the change of one thing on another? So in my simulations, I looked at a change in one of the first systems principles of a change in purpose of a system, a technology, engineer system, an ecosystem. What is the change in the purpose of that system? What is the change of the structure of the system? And what is the change of the behavior of that system? And can these things actually cause innovation? Next slide. Next slide. Thank you. And so simple models are very important, but simple models give us a basic idea of causation. And truly using a graphical model is a way that not only do you get the idea of changing and innovation, but you can also now start predicting what happens, what if scenario. what if something changes by a certain percentage versus a smaller percentage, or what if two things change relative to each other? And in using model-based systems thinking, it gives us the ability to do the what if scenarios, which we can't do with correlation. Correlation just says these two things are related, but they don't give us the what if. And so in looking at in my research, the causation of innovation, as I stated before, I looked at the change in purpose, structure, and behavior and did some what if scenarios in causal inference. And causal inference requires us to use directed acyclic graphs to get the inference of what is what will be the behavior of something if something else changes within that. Next slide. Causal inference in looking at directed acyclic graph stuff give us a linear relationship of behavior between changes of two variables, two events, or even within two systems. But as we know, with model-based systems thinking and within within systems engineering, complex systems are very dynamic, and they dynamically change over time. And so looking at causal relationship in the dynamic regime is a necessity in trying to understand how things evolve over time, and not just how things evolve at one particular instant of time, like what happens in causal inference in directed acyclic graphs. So cyclic graphs that we use in systems dynamic actually brings together the model-based systems thinking of looking at causal inferences and also the systems principle, as I said, which is a very strong and a very powerful tool in a way to understand how to first design systems, how to predict systems, and how to look at systems behavior, even predict failures of systems in the future. Next slide. So I built a model that shows what happened when a researcher's paper, idea, or anybody's research in systems and science and technology is adopted over time, and that effect of the adoption over time, and how that can be used to show if it's going to be innovative, non-innovative, and what the effects are on the adoptions and the adoption rates. And so this is a simple model that I put together for my research and one aspect of my thesis research idea. Next slide. And what this has shown is that the complexity is dynamic. There is an evolution that can happen within an ecosystem, and that ecosystem and the complexity of the dynamics of that are due to the feedback within that system. And one of the most important things about model-based systems thinking is understanding that systems do have feedback, and these feedback have interplays over time. And if those aren't addressed, especially within the system that I am in, which is in the Department of Defense, then it is hard to get prediction of what can be useful for stakeholders. Next slide. And in seeing that, of course, we see that the feedbacks cause nonlinear behavior. These nonlinear behaviors are the behaviors that we wish to predict over time. I dare say that a lot of our correlation thinking that we have when we first look at systems and design of systems, for us, it's easier to think in a linear manner. It is harder for us to understand and to delve into the complexity of the nonlinear behavior of systems. But using systems dynamics and model-based systems thinking, we can get the tools to do that. And these tools for discerning what the nonlinear relationships are useful not just in systems engineering or the engineering fields of technology, but they can be used in all fields, from medical fields to social engineering to environmental engineering to the complexity of I think what we're getting ready to go through now, which is the political system. So, you know, these things are very useful. And when you think in models versus correlation. Next slide, please. Shall model-based systems thinking be discipline agnostic or specific? And so this is a, you know, question for the group. Should it be agnostic or specific? My answer to this question is no, it should not be. As I alluded to previously, the disciplines of thinking in models can be applied to any field, any endeavor of research, or any way field of understanding. It is my personal belief, and I wish to get the belief within the group here that that's online, and at least to start the discussion, that I believe model-based systems thinking is a philosophy, and this philosophy is useful for discovery and the formation of knowledge. And when you're looking at the formation and the discovery of knowledge, then you really need to have some sort of, at least a simple model in your head of why something affects something else, cause and effect. And cause and effect comes back to using model-based systems thinking in the same realms of the scientific discipline. You know, scientific discipline, coming up with the hypothesis, building a test for those hypotheses, either a simulation of the test or a scaled down test, and then taking the knowledge from that test and reevaluating your hypothesis. And so in that sense, and in that vein, that is model-based system thinking. And so I like to open that up to questions. Does anyone actually believe that model-based systems thinking, or thinking that model-based system thinking is a useful way of understanding the complexity and the dynamics of today's systems, social system, and environmental system, or any other systems that we have? Any questions? Any observation from my presentation?
So I'll be talking further about, I'm the next presenter. So Quinn, I'll be taking a slightly different look at the same question and try to answer it saying, I don't want to give that away, but being discipline agnostic is good, but it depends.
I agree, and I agree 100%. And thank you, Ms. Chappell. Well, if there's no discussion for that, we'll go next into Ms. Chappell, who will definitely give us another aspect of how to use model-based systems thinking that is I hate to say non-engineering specific, because in my mind, everything is engineering. Even if you're a gardener and you're growing plants, you know, you're engineering something to get a specific effect out of it. So, Ms. Chappell, you're up next, and
All right.
thank you.
Thank you, Quentin. Yes, so I think I introduced myself earlier. I'm also a senior program officer at the Office of Naval Research. And although I'm not talking about this right now, I do use model-based systems thinking to enhance model-based systems engineering and basic systems engineering. And I'd like to make a comment about that. I meant to do it earlier, but if you look at model-based systems engineering and to be able to use it effectively, you have to use model-based systems thinking. That would be my position on that, because you see a lot of this, and I know Mr. Dano mentioned that, you know, I also work in DoD, and we tend to be very confused about when and where we can use model-based systems engineering. We tend to want to do it late in the life cycle, though it's actually its most effective use is early in the life cycle, where you can do the trade studies and figure out and predict what the behavior of the system is going to be and what happens if you change. And to be able to even capture all the things that you need to do for model-based systems engineering, you have to employ model-based systems thinking, or you're not really going to have a very good model. So just a comment about that. What I'm going to be talking about is the physiological application, enhancing fitness with model-based systems thinking. And I'll walk you through how I've used the tools and how this to handle the complexity of the problem. Model-based systems thinking is I would say, the best way to do that. If you could go to the next slide, please, Golan. Golan? Thank you. So, we all have people telling us, oh, exercise is great for you. And a lot of us even understand that. We know the benefits. There's, a lot of them use it for weight management. Some use it for improved health, strengthening bones, reducing risk from diseases, even mental health. But to do that, you have to exercise. You have to do it daily, or at least several days a week. And to really maximize that effect, you pretty much need to increase your intensity of your exercise at a level for a certain amount of time. And this ability of a body to sustain exercise for a long period of time is known as physical endurance. And each person's physical endurance is different. And endurance is measured in many ways. I'm going to focus on the physical part of it. So how do we do that? Training enhances that. And when you train, it causes a change. When I say train, I mean exercise over periods of time. You cause a change in the physiology of the body while it interacts with various environmental and other variables. And these all interact in an extremely complex way as your body changes over time to improve, hopefully, your fitness level. It can decrease too, based on some initial fitness level. If you could go to the next slide, please. So where is the complexity coming from? The complexity comes from the fact that there are feedback loops between not only the physiological parameters that affect endurance, but also the interaction with them and environmental factors, such as terrain, altitude, you name it. Diet affects you, sleep affects you, which is why there's not a one-size-fits-all answer for endurance. And these interact in a very complex way, and they also interact over time. So it's really hard to gauge what a person's endurance is because of these multiple reinforcing and balancing feedback loops between all these variables. And key to this, the concept of endurance are three physical systems that we know of, but we don't think about. And they are the cardiovascular system, the muscular system, the pulmonary system. Now, the pulmonary system is responsible for breathing and oxygenating the blood. And the cardiovascular system is responsible for pumping the blood and transporting it through the body. And the muscular system is responsible for utilizing the oxygen in the blood to create work and some sort of movement using fuel, which can be different things like fat or sugar, depending on what your intensity of your exercise is. So the intensity drives how much you use your fuel and how your body works. So as you exercise harder, your body needs to breathe harder because it's trying to provide the oxygen needed by the muscles to break down the fuel to provide the energy needed to actually propel you forward, whether it's walking, running, biking, you name it, any kind of physical exercise. And when that is happening, there's something that's produced that's known as a lactate, which is produced. If you go to the next slide, please. So as you increase your lactate, there are different levels of endurance that are created depending on how quickly you can remove this lactate, which is a byproduct, which causes the burning and soreness that you typically see when you exercise too hard. So to be able to handle and improve your endurance for any person, you need to change your mental model. We've talked about mental models earlier, and you can use the iceberg model, to actually figure out how do we get the best leverage to improve your endurance. So I applied the iceberg model as a first cut. And when you look at this, you realize that you have to improve your mental model of how you can adjust your training to achieve whatever your desired exercise goal is. Meaning, how do you move from your one physiological state to a better physiological state? And the way to do that is to train, which improves your physiological structure and state of fitness. And when you do that, you improve your physiology by better training habits. And that leads to you being able to go further, go longer, or maybe even participate in the race if that's what you want to do. So here's a simple example of how applying the iceberg principle, which is one of the tools of model-based systems thinking, can get you thinking about how to improve endurance. If you go to the next slide, please. So here are some key fitness physiology dynamics. I'm not going to talk a lot about them, but a couple of things to keep in mind is that I mentioned, the production of lactate, and when your body starts producing lactate as you're in your low intensity exercise, you're typically able to remove that lactate with the blood. But as you increase your intensity, you're not able to keep up with the production of lactate, and that's known as the lactate threshold. That your body produces more lactate that you can remove, and you can maintain that up to a point, but then you get into a point where your body runs out of oxygen. It starts using the muscles around of oxygen and have to use fuel in glycogen in your muscles to do that. But one of the indicators of your lack of oxygen or also is what's known as a VO2 max, which is the max amount of oxygen that you can actually utilize. Because it doesn't matter how much oxygen you have in your body, you will, if you cannot utilize it effectively, it doesn't do you a whole lot of good. So you have to think about all the different things, and there are other indicators like your heart rate and resting heart rate, maximum heart rate. And I'm not going to get into all the physiological stuff, but they are all indicators that can help you build this model, and you have to consider all this when you're trying to figure out how do I improve the endurance from one state to another. If you go to the next slide, please. So I put together, and this is just one piece of the puzzle. I have a bigger model. This just to be able to explain this. This is a model, causal loop diagram of aerobic endurance. And again, if you go back to what Ghulam put forward, this is one of the tools we use to look at the causality and the interactions and the feedback loops, both balancing and reinforcing between key variables, that are part of your system. So there's a huge interaction between, say, training intensity and heart rate, or your body fat affects how well you can exercise and how much you can utilize the oxygen that you have. And there are a lot of other factors that feed into it, such as age, gender, alternate physiology. And if this was easy, we would have already done it. We have all kinds of training plans out there for people who want to improve their fitness. And a lot of people cannot follow them because they're one size fits all. There's been some increase in use of say AI machine learning models, but they just look at patterns from before and then still prescribe a specific plan. So that doesn't really help people who are not really exercisers. It helps maybe elite athletes to some extent, but again, they are very cut and dried. What we need is a way for anybody to take their current initial fitness level and be able to improve it to whatever goals they have, or build it up over time. And there's not a good understanding of how to do that holistically. There's a lot of domain-specific knowledge on each of these individual things, but there's not anything that puts it all together, which is why people have a lot of trouble following training plans. A lot of these things do not even consider things like what happens if you get injured, or you have some health issue that you're trying to deal with. And exercise also has been recognized as a key to longevity and dealing with keeping diseases at bay. So it's not just for if you're just doing it for fun. You also need exercise to maintain your health. If you could go to the next slide, please. Okay, so I use the next. If you're following Ghulam's MBST framework. I pretty much followed it. I'm trying to show you how I used it. So I did the causal loop diagrams, and then I matched reference modes. There was data from studies about 6 weeks of moderate endurance and high intensity intermittent training. And the change in VO2 max over that time was measured. And I matched those reference modes with my model, which gave me a validation of, that it does model the system that created this. I matched many more reference modes. This is just going to give you a taste of some of the reference modes that I matched. If you go to the next slide, please. So once I matched it to various reference modes such as VO2 max or training and other things, I had a good indicator that yes, it is able to generate the system behaviors, and so I have a good model of the system, and now I can use it for prediction. And so I started using, this is just one piece of the model. I started using this for what can we do to predict things that we haven't thought about. So one of the things it did predict was the gender difference in VO2 max increase. And what model does show that it's significantly low increase for females versus males for the same training period. No matter what their fitness, this is for the low fitness level, but it's true also for high fitness levels. I looked at for low, medium, high fitness levels and various levels of intensity. And it makes sense when you start thinking about the layers below it, which is the female cardiovascular systems are always usually smaller than male cardiovascular systems, which means your heart doesn't pump, your heart is smaller and you're pumping less blood to your muscles, and female physiology is usually different than male physiology, which is why it takes longer to increase your VO2 max. But that does not mean that you cannot improve your endurance overall. You have to do it relative to your initial endurance capability. You could go to the next slide, please. So what I showed earlier was, you can make predictions. There was other predictions you can make as far as overtraining and things like that. And this small model that I showed you is part of actually a bigger model, which can be used to predict your overall endurance while you're training over a long period of time, because you don't really see a lot of these nonlinear behaviors till you train beyond a certain point of time. If you just do it for a couple of weeks, you'll see some changes, but they're mostly linear. But as you start training over periods of 6 weeks, 12 weeks, and long periods of time, you will start seeing a bigger change. And it's not a direct correlation, as Quentin mentioned. There's a lot of interacting feedback loops and a lot of nonlinear complex behavior that you cannot account for unless you model it in this manner. So this holistic approach looks at these multiple perspectives and connects both the fitness and the physiological systems with our environment systems, and other things like diet, exercise, recovery. And you can use this endurance approach, you can tailor it to your initial endurance capability and fitness state, which is right now a difficult thing to do. Because this model also looks at things like non-typical factors, something like detraining. What if you get injured and then or you cannot train and you have to take a break and go back? There's specific data showing that it does reduce your endurance. You can bring it back up, but there is time frames related to that. Terrain affects you, altitude, weather, diet, recovery, and variables is the thing now we all used to, things like watches and heart rate monitors, which give you data which affect you. There's also a mental aspect of this, which I'm modeling, which I have not shown here. I'm using agent modeling to look at the psychological aspects of training with somebody or in a group, and also during race day, how does that affect you and your performance during a race? So this is a real life application that shows anybody can use to improve their fitness level. It can be used by health professionals, it can be used by coaches, it can be used by by anybody. But the whole point of all this is this would not be possible without model-based systems thinking. Go to the next slide. So there are some key takeaways. The complexity of endurance dynamics cannot be captured by linear thinking, and does require the use of model-based systems thinking because it provides a holistic perspective for everything that's involved, all the balancing and reinforcing feedback loops that interact with each other over time. And as your body changes its physiology during a training period, and also if you look at even during a race, you have a smaller microcosm of that. And what helped was the use of these rigorous tools. You saw me use the iceberg model. I use reference modes. I use causal loop diagrams. I use inferences to anchor the model. I had to use talks and flows to define the system dynamical model. And I'm also using agent modeling to capture the mental aspects of improving endurance. So here's a prime example of using MBST for a non-traditional application. So let's go to the question. So shall model-based systems thinking be discipline, agnostic, or specific? And as I said before, it depends. It's especially when you're looking at a multidisciplinary problem like I'm looking at. The tools are discipline agnostic, which is helpful, but you have to be able to tie in the multiple disciplines and the specific knowledge together and weave it together and with the interactions as part of the model-based systems thinking when you define system dynamical models and you look at causal inferences and you look at sensitivity and what affects the performance and of these loops, and which affects how your system behaves. So that's all I have. I just want to see anyone have any questions, any thoughts. Happy to discuss.
Quick question for you. In this particular instance, because you alluded to the fact that the mental piece, the psychological piece, could have an impact on what's going on. And normally, I think when we think of model-based systems, anything, we're thinking of very factual, concrete, I can get my hands on something and measure it. How did you account in your work for something that might be, while having some predictability, is a little softer or a little harder to get your hands around, just because of the nature of you're dealing with humans primarily in this situation?
Yeah, I'm still working on that, but my plan is to use delays. So things that you can affect delays based on if a person is training and they're not doing well, they know if you can predict that they are having trouble, they will automatically not achieve the gains that you would expect as well, and vice versa. If they think they're accomplishing the gains, they will maximize their ability to get the gains in endurance as they go forward. Does that answer your question?
It does in part. I guess what I'm looking at is you're also, I think, looking at motivational factors. You're looking at psychological pieces that maybe today I'm really up and so I'm going to do much better in one of your models, but another day I may be depressed or sad because something else happened in my life, and so I may not be trying to strive quite as hard. And I was just curious as to, have you seen whether that has a lot of impact on the mental models that you're doing in terms of how do you get people to keep making progress in this overarching thing you're looking at?
Yeah, Michael,
I'm still working on
that. What Ms. Chappell's also doing is she's looking at agent-based modeling. So if you're familiar with agent-based modeling, you can capture a lot of those psychological implications and factors and how the interactions of people with people, or the interactions with people with their mental capability influence how they behave. So agent-based modeling is really good for behavioral factors. And Ms. Chappell has a really good movie that can show what happens for endurance activity if she wants me to show it. In which agent-based modeling can capture all those aspects that you were asking.
The point is, and Kun brought it's a good point. The agent-based modeling gives you a pattern of how the interactions affect the mental state, which can then be factored into the bigger model. Do you see where I'm coming from? So use the agent-based modeling to figure out, and then you feed it into that. I think that's what you're asking.
Yes, you've answered my question between the two of you, so thank you. Like I said, I'm still learning a lot about this, so I appreciate your patience with me.
No, we have used different tools, as Dr. Shahroudi said. Yeah. We use different tools for different purposes, and we weave those together. We choose the tools that make sense to inform us.
Yeah.
Well, there's a question from Laura Ekman. Do you have a model for understanding the level of uncertainty you have with respect to capturing all the contributing factors to the system's goal?
Yeah, another good model for capturing uncertainty. I think it's just not just for what Sarah was discussing, but for also what you discussed and what Kirk will discuss and what Dr. Trudis discussed is Shannon's information theory. Looking at the entropy of uncertainty is a really good model, at least to start with conceptually, how to capture the uncertainty in any complex system. The information theory can be applied across the board, I think, not just for engineering aspects, but as I mentioned before, for a lot of different disciplines, medical, biological, environmental, social, because information is what we share. We share information between each other. And in that information, certain knowledge can either be gained or it can be lost. And so that in itself can build entropy within a complex system. Good question. Awesome question.
Yeah. Thank you for wonderful questions.
Would you guys like to see a movie of what Ms. Chappell was discussing? I think Gollum, you
I'm
want
good
to
to see it.
Yeah, let's do it.
It's very funny. It's very
Or if you
funny.
have a
Yeah.
link, I can
Thank
show
you,
it.
Quentin. Yeah, it's
Excellent.
really funny. Go for it. Do you have it, Golan?
He's giving me screen share.
Yeah. It's actually very humorous.
Okay, any other question while we are digging that up? I noticed a few people came in later.
Well, as this marinates, as I call it, if you have further questions, feel free to reach out. We have our email addresses. Happy to answer, because sometimes you think about it and later like, oh wait, what about this? So feel free to reach out to us. We're happy to answer.
Yeah. Yeah, I think we're not trying to be, not necessarily trying to talk about the domain-specific aspects, but it's interesting that it's in all this big variety of types of problems, we are able to, real-world issues, we're able to increase our understanding of the complexity and so improve our chances a bit better. Golam, are you still digging something up?
I was waiting for a link from Quentin. Oh, here we go.
Oh.
All right, let's do it. Let's
Wow, what a beautiful day. Listen, everyone cheering. This is going to be great. Months of training is paying off now. I'm hydrated, glucosed up, and my mental game is on point. Let's do this.
That's what we need.
Okay, so I'm a little behind on my normal pace. No big deal. Just keep going. And I think I missed a spot on my thigh with my body glide. Sure, that won't be a problem. And I don't need to stop for water just yet. Oh, look, here come some hills. That'll be fun. Wait, I'm not even halfway through yet. Feels like I've been running forever. What's with all these hills? The whole course hills? I think it's going to be tougher than I thought. Where is everybody? Am I still on course? I haven't seen a water stop in forever. Why didn't I get water earlier? Well, it's just me, myself, and the road, I guess. Nothing left to do besides confront all of my inner demons. I am going to die. Why did I ever decide to do this? My thighs are raw like two hams, and I think my toenails just fell off. What else could possibly go wrong? Oh, great runner's trots. Well, at least I haven't hit the wall yet. Die. Whoa. I've never been so tired in all my life. Even my teeth are tired. I think I should just quit. Stop touching me, you jerks! No, I need to power through. I didn't train for months to give up this late. Time to dig deep. Think of that Olympic runner who finished with a broken leg. That was really gross. But the point is, if he can do it, so can I. Now, come on. Finish line is right up there. 1 foot in front of the other. Yes, I did it. Oh, this is the greatest feeling in the Carry me to the car. I am going to eat my weight in pasta.
So, as you can see, to avoid what he was dealing with, training definitely helps you. You can see the difference of how the mental model, he reached in and towards the end, and the mental discipline helped him get to the end point. And so yes, all the things you saw there, I have also experienced, and I'm sure anyone who has done any sort of longer race, 10 miles or 10K or further, you've seen this. So this is what I'm trying to do to help. Okay, you see Kirk will give you a very interesting, different view of how systems thinking is an essential concept and where we are going in the future.
Thank you. Next slide. So my position is essentially that why are we even having this discussion? It's because of complexity. We're trying to solve things that we can't just look at with our brains and see the answers. We're usually trying to solve those with respect to something,
I love that sentence.
The probability of mission success or side effects, cost, political gain, political resistance, who knows? But what it comes down to is complexity is in the eye of the beholder. And this can kill people if we don't recognize this. Typically, we say the word complexity, but we skip the with respect to part. Like the Apollo 1 requirements had a requirement in there that the hatch shall be simple to operate. That got interpreted as, well, gee, bolts. I mean, it can be more simple than that. Until there was a fire in the cabin and we couldn't get the crew out and they died. The next Apollo hatch looked like a freaking Rolex watch on the inside, many, many gears, several hundred moving parts, arguably very complex, but it was very easy to open. The point of that being the sad story is that the complexity, we always need to ask, what are we trying to be? What is the complexity? It might be P equals nRT if all you care about is the pressure in the tires when you land. If you're making a hypersonic intake, you are not going to be using P equals nRT anymore. You're going to be tracking molecules. We have to know which one we're talking about. So back in the day when we had mistakes like this, the consequences, although we killed people, they weren't that big. We probably weren't killing hundreds or thousands or millions of people. But now we're starting to face problems of immense scale of consequence, and we're starting to face problems with immense scale of resistance to change. This is not a very good place to be as far as trying to solve it from the engineering perspective. But this is exactly the domain of system engineering, is solving these massive problems from an engineering perspective. So it's apparent that the methods we used before are not going to scale. We're seeing that already. You've experienced this. You probably made some really cool engineering report and went up into the C-suite and vanished because you thought the problem was to maximize probability of mission success. The real loops, the ones you ignored, it was to maximize profit, maybe to maximize somebody's move into another position. Who knows what they were? But we weren't playing in that game when we were doing the engineering. Now we need to see a lot farther because the problems are not just where our solution gets shelved, it's where your solution or resistance to solution gets shelved. And then somebody dumps 1 million tons of sulfur into a volcano and has unintended consequences, and we have a global extinction event. In order to argue for or against, whichever way you need to argue, it's going to take irrefutable bomb-proof logic in your pitch deck to argue something that makes the consequences and the power, the impact of those consequences absolutely, unavoidably, inexorably point made. And how do you do that? How do we always do that? We do that with tools. MBST in particular is what I'm proposing here. Next slide, please. Also, I love dialogue. Feel free to interrupt me at any time. I'd much rather have a great conversation than get through my slide deck, although they're all great slides, of course. So getting fluent in the tools like system dynamics, for example, is really tough, as has been explained before. And then on top of that, the typical models we have might have a few loops. We saw one with 8 or 10 earlier. But real models have thousands of loops, if not millions of loops. That is enough to make conventional tools not scale very well. But now we have AI and ML. We're talking now, a way to look at AI as an engineer is that like an LLM, is a trillion parameter curve fit to all of the words ever written and stored on the internet. That is one heck of a curve fit. That's going to have a lot of capability that you're not going to get with our typical curve fits that we're used to with tens or hundreds of parameters. The other thing that really interesting that happens with that I've found is that as an engineer, you tend to not want to have a trillion parameters. You're thinking, man, I'll never understand what the underlying physics are. I want a model where the model's parameters kind of fit to the problem domain. We like that, but we need to get over that to attack these infinite scale problems. The large AI and ML solutions are probably never going to be directly scrutable by us, but they are going to provide insights that we can use to solve these huge problems. I'll give a couple examples of this later about what I did 2 slides later, I think. Next slide, please. So this is the framework you saw earlier. I've annotated it with where we can use AI and where I'll demonstrate the use of AI. Even in the earlier phase, when you're just conceptualizing your problem, the AI can provide substantial aid in opening your mind up to the possibilities of what your problem domain is. If you haven't had a good conversation with an LLM recently, I strongly encourage you to fire it up, have a short discussion with it to set its mindset into ST and SE and MBSE, and then tell it your problem and ask it to critique it. Literally type that string in there. And if you haven't tried it before, you'll be truly impressed with what that can do to open your mind up to the possibilities. The next place we can see it in those curves, those 6 classic curves, I actually did this. I took the output of several thousand models and ran them, and then used an ML approach to match them against those curves. And who would have thought, but about 3/4 of the curves in those models actually do follow those behaviors. But I did that with the ML. I didn't like handcraft this thing and do a whole pile of curve fitting. I let the machine work that out, which was a struggle to my 20th century engineering nature, where I want to go in there and handcraft the equations. But for the 21st century solutions where we use these tools, we need to get past that nature. Then we go after the question of, okay, what are all the bits and pieces of our model? There's a notion of a model being composed of molecules. These are little snippets of behaviors that lead to those curves in block 2 glued together. I did a bit of work also on decomposing models and then reconstructing them, going from the curves to the likely set of molecules to construct the model. The idea being here that is you come in as a modeler, probably you don't want to spend all your time trying to dig up the root of your model. What you're interested in is getting insights into the problem you're trying to solve. So this suggests the possibility of a workbench that can help you get past that phase, get immediately into your problem domain rather than in your modeling domain, and put more of your attention into solving the problem and less into trying to develop the model. I also use that to construct the structure and the behavior. I'll show an example of that. And then finally, the bathtub. This is an important point right here with respect to a point I'm going to make in a moment. That bathtub is an integration, like mathematical integration. Typically, we in engineering would use differentials, but system dynamics writes it as an integration. It's easier to explain to people with that bathtub model. And it's also numerically easy to solve integrations than when you get into differentials, you get into all kinds of endpoint issues and stuff. But let's go to the next slide and away we go. So I took a model, I took Quentin's model, in fact, and I asked the AI, first I gave the AI Quentin's model. Now it's important to note here, I'm not using a whole pile of rocket science to do this. It's quite to the contrary. All I did was primed up the AI with a few notational ideas like acyclic directed graphs, for example, that you'll see there, and the notion of balancing and reinforcing. Then I gave it Quentin's model, which I also let the AI come up with what is the purpose of Quentin's model? I didn't tell it the purpose of Quentin's model. All I did was gave it the variable names in his model and some of the relationships in his model. And then with the prompts I gave it, this thing on the right is what it came up with. Now, it's not really important to go over that a whole lot, but it is interesting that it did a fairly good job of disassembling his model and explaining what's going on with it. Then we got a little more interesting in our prompts. Let's have the next loop, please. Next slide. I should have put this one, I got out of order here. This is where I took that big old mess in the upper right corner is all of the behaviors in about 1,000 models. Obviously I scaled them all into a uniform scale. Then I ran them through the model and let it come up with some fits. Now it's also, I didn't come up explicitly with the fits in here. It had a lot more to work with. These are the fits that explained a whole lot of the behavior there. It was interesting that it came up with a whole lot of periodic behaviors, but if you eyeball it, you can see that even though in those 6 behaviors, the periodic nature isn't really stressed, but obviously in real life, there's a lot of periodic behavior that needs to be accounted for. I'm going to do some more work on this by convolving these across the curves rather than looking at the curves as a whole. But the point of that being that a lot of insight was gained. I didn't have to do a lot of work to do it. And we've got the start of going directly from a behavior curve and going back to a model that explains that behavior. Next slide, please. This is Quentin's model again. Now this time the thing was, here's Quentin's model. I gave it some pieces of it and I said, now let's critique this thing. What are some missing curves? Now, admittedly, I gave the AI a bit of a bias to go after this, but you'll note that the AI determined that there's an unaccounted for feedback loop is that if there's a profit to be had from an innovation, that's going to make the innovation happen faster. And if there's marketing or lobbying, that's probably also going to increase it. These things were not in Quentin's model. I didn't decide to put them in Quentin's
I just want to
model.
say, Kirk, we're
yeah, I know. Okay.
Just
Yeah.
want to make sure you're aware.
Yeah. Okay. The takeaway of this is if you're not using AI or investigating it, go do it. Next slide, please. So the point of this, the problems are getting bigger, but we can't ignore human behaviors. Humans are probably the most complicated element in any system, but we system engineers typically ignore that. We can't. Don't do that anymore. AI and ML can help a lot to help penetrate that. There's a whole lot of human behavior encoded in AI that's there to be mined if you want to explore it. This isn't really what us system engineers are good at, but it's out there available a lot more easily than it was a few years ago. And it's quite practical to use AI to do these things. Nothing I did here was any rocket science stuff. It wasn't that hard to do. Next slide, please. Why is SD penetration low? I believe that's because we typically use it on technical systems. These are continuous, you can integrate them, not a lot of stochastic behavior. But real systems that people face, especially non-technical people, have a whole gigantic pile of nonlinear stochastic behaviors because of humans. If you're a non-technical person and you try and apply SD, you're probably going to fail because humans don't follow differential equations. We're a lot more complicated than that. Even if you could, I argue that a modeler is not likely to put in his model, oh, look, here's where the C-suite's going to trash my model because I'm threatening the profit of Boeing. Nobody's going to do that. So it's extremely challenging. Then the model's going to be incomplete. The bottom line of that, you put a lot of work, you get a little impact. So adaptation is going to be limited. But I don't think it's hopeless to deal with this. We have AI available now that has a whole lot of insight into human behavior that we will never know, but we can exploit in order to enhance the quality of our models. Sorry I had to rush that, and we can't have any conversation, but here's my slides.
Well, you got 1 minute for to put any questions in. I think what Kirk showed us is that traditional tools that like system dynamics, that is actually pretty tough to learn and do. It's possible with AI, machine learning, and other tools to really scale up and help with the complexity of tasks. Anyway, we as a team, we appreciate the opportunity that you gave us to share our progress with you. And if you think of something now, please go ahead and ask. If otherwise, please let us know. I think the recording of this will be available, and you can always email us. Yeah, we'll just be very happy to hear anything back. We are interested, excited about these topics of how to use all these, we don't care about a particular modeling method. We don't care to push a particular paradigm, but how would we do systems thinking at the next level, basically, using models. All right. Are there any questions before we close? It's exactly on time. Yeah. All right. Thank you, Laura. Appreciate it. All right. With that said, I think it's actually been a long day here in Dublin. We started at like 7 a.m. for the speaker's breakfast. So thanks to all the panel. I miss our normal weekly interactions. So hopefully we will get back to that after this Ireland trip. The panel, anything you want to say before we close?
Yeah, how's the weather?
Weather was terrible last week, but this week it's starting to get good. Yeah, it's warming up. So it is, when you come here, you have to learn to appreciate, to use your time and enjoy anything, because it's very unpredictable. Windy and rainy very often.
Well, thank you for the opportunity. I enjoyed talking about systems thinking and sharing some of the work. So thank you, everyone. Great questions. Thank you again.
As one last thing, wondering if you have any recommendation for resources to learn more about model-based systems thinking, and if anyone wants to look it up, what would be good resources to look into?
So we're working on a textbook, this team, and plus Jill Spies, who is not here, but I shared some of her work earlier. We're working on a book on systems thinking, and it's intended for introductory kind of undergrad plus, I should say, because of feedback from a lot of people we get when they come through, when they do things the hard way. They say, well, why don't you teach this earlier so we don't have to unlearn all these bad habits later? So that's the intent of that book. So I hope, I don't know, Ghulam, if you had that the title page that we had available to you, but we could potentially, if anyone's interested, please email us, and we're looking for people to look at that advanced draft copy of the book and to give us feedback. So if anyone's interested, please let us know. Other than that, watch this space. Everybody here is into publishing too, and we will probably have 2 or 3 papers between now and end of the year on these various topics. And if anything here excited you or interested you, just watch for these names, and you will not be disappointed. Unless there are any last minute questions, let's see. Are there anything in the chat box? Thank you. Well, okay, great. Well, then as much as it hurts me, let's put this to a close.
Here's the.
Thank you.
Enjoy the rest of the conference.
Thank you, panel. Appreciate it. Bye.
Thank you.
Bye-bye. Thanks, Jill. I really appreciate the computer use. Leaving.